back to oscillation. And then you multiply that by delta alpha, so I. If that is less than epsilon, that's called it's called the Riemann-Stieltjes condition. If there's the alpha here, if it's just an xi, it's just Riemann's condition. And if that's true, if you can always find the partition given any epsilon, so that's true, then that implies F is, in this case, since it's sort of Stieltjes, so the soup inf business is a somewhat later invention of the original integral. That's due to Gaston Darboux. And didn't it make it kind of easy to understand? You go above, you go below, you refine, you only get better, and then pretty soon those things have to come together somewhere, or you have no chance of being integrated. So you would start with this and show that the sums then have to approach each other. Your actual function, the contribution to a Riemann-Stieltjes sum would be stuck in between the soup and the inf, right? If you wrote this thing out, the soup times delta alpha would be higher than the function evaluated at the tag point times delta alpha, and that would be higher than the inf times the same delta alpha, right? All the way across the board. So if the two guys on the end are arbitrarily close, the guy in the middle has got to find the limit somewhere. That's the principle behind it. Anyway, so we got that. Generally, we go back to
What theorem is this?
I don't think he actually proves the linearity. That's what we're doing. He proves something about monotonicity. By the way, Dave, Euler's summation formula is 12. And no, he doesn't, he skips a lot of stuff. The Stieltjes chapter is short. He doesn't show it. But we ought to show it. I mean, we ought to be able to show something. If you have a copy of Root, Baby Root, that's certainly there. If you want to study the Riemann-Stieltjes thing, the Baby Root is good. Everything is laid out extremely detailed. They call this book Baby Root. It's Walter Root, a famous analyst. I think he did by now. But this book is used. If I were teaching analysis, this is the book I would use. And then Grown-Up Root is a big green book that also, this is just real analysis. The green book does complex analysis as well. This is a senior first-year graduate book, and the other one is a second-year graduate analysis. It's pretty stiff. I beg your pardon? I don't know. I never get to teach analysis. This is the closest I ever get. Unfortunately, I am an analyst, so. Oh yeah, but that's complex analysis. No, we're not going to use it. We're going to use Fisher. I'm going the applied route there. I don't know. I think people would just, I don't know, that we can get bored. But, revisiting all this in the context of complex numbers is very technical. I don't know.
Is there much difference?
Oh yeah, huge difference. Gigantic. Are you taking complex? Yeah, it's a great course. I was always impressed with the power of what you're doing. Complex analysis revisits every issue that's real analysis, and then you discover that there are certain very powerful theorems available in complex that have no counterparts at all in real analysis, like the residue theorem, where you do really potentially very complicated complex line integrals by basically, well, the residue theorem says it's kind of off somewhere. You know what a line integral is? Well, here you are in the complex plane, and a function that you take the line integral of around the region might have singularities within the region. And the function has what they call a Laurent expansion at each point at these singularities. And a Laurent expansion is just like a regular power series expansion with a front end that's usually finite. It's not finite, that's a big problem. But it's finite front end called the principal part. And there's one coefficient that you can pick out of a Laurent series. You multiply that by 2 pi I and add those things up, the ones that are inside the curve, that's the integral. I mean, it's unbelievable. It's unbelievable. I mean, if you try to do the line integral from scratch, it would take you all day. You'd make all kinds of mistakes. But if you just sum up the so-called residues multiplied by 2 pi I, you get all these fancy formulas, stuff that you just like. How did they do that? Kind of stuff, and then it comes out of complex variables. And maybe in the past I've gotten to conformal mapping, which is a great application. So residue theory and conformal mapping, that's where I'm going to go with complex. So we learn just enough stuff to take off. You know, we get our license and we fly for a little while. Conformal mapping is you have a complicated problem and you change the domain over which it's defined into a simple one that you can solve the problem in. I put this on a test a while back. Sorry, this is just a gigantic aside. This was the problem. What is it?
Snodgrass.
Snodgrass?
Yeah, it's the word I put on her condition.
Okay, so it's like...
supposed progress.
Okay. Anyway, here's a pizza oven.
Oh, yeah.
Okay, here's a pizza oven. And I had a temperature profile along the edge of this. I think actually the pizza oven was like this. There's a temperature profile. You put the origin there. You map this into the real axis, and there's a zone here. This thing then gets mapped into a piece there. You solve the temperature problem. Temperature as a function of position in the upper half plane, which is reasonably easy to solve with Green's functions. And then you inverse transform back to the true geometry of the pizza oven, and then you can answer any place inside the pizza oven, what's the temperature? So it would be very difficult to do that if you didn't have these methods available. You know, you'd have to set up the temperature distribution as a harmonic function, and right, you've got equitemperature lines with the isotherms in there, and then the heat flow is perpendicular to the isotherms. You can see the same thing in the weatherman. And you would have to start with the boundary conditions here and back into what the temperature. It's not that it can't be done, it's just that complex variables and conformal mapping allow you to do it just very, very easily. And it's like a table of integrals. People have gone and looked at various geometries and recorded the functions that you need to map it into the, you do two things. You map it into the line, the upper half plane, so that's the real axis, or you map your domain into a unit circle. And then it's easy to solve all kinds of problems with these two domains. And then you throw the lever in reverse and go back to the real domain. So I had a problem on a test once where this Chinese professor, not that that's relevant or anything, but it was an oven or some temperature problem where this was a temperature T1, this was a temperature T2, and you had to find the temperature at any point in here. So you use the arctangent function to straighten this out, solve the temperature problem, and then inverse map to get back here. Then you can pick off the temperature. Anyway, that's the kind of thing you do.